Good day, my fellow learners. Sitso is back. Today we are going to do the new concept of what? Of electric field. Electric field. By definition, the electric field state, it is the region of space in which an electric charge experience a force. This is a simple definition of what? Of electric field. Then bear in mind that the term electric charge, it refers to the following charges in this scenario: the positive charge together with the negative charge. Then now, how are we going to represent the electric field lines for these given charges? Firstly, we are going to start with a positive. As a learner, you must know that the electric field lines for the positive charge, they always point away from the charge. But for this negative charge, they will point, they will point towards this charge. And another thing that you must bear in mind is the electric field lines, they are stronger, closer to the charge. But weaker away from the charge. Then now we are going to consider a situation whereby we have two charges, like charges and unlike charges. Firstly, let us take two like charges, positive together with a positive. Then how are we going to represent the electric field line? It is so simple. They will bend like this. Then we continue by drawing arrows pointing away. These two charges, they will repel each other. Two like charges, they repel each other. And bear in mind, when drawing the electric field lines, there has to be a space for two like charges. Like this. You see? Like this. There has to be a space for like charges. Then we also have a situation whereby we have two negative charges. Field lines will always point towards the negative. And bear in mind, we have to have this space in between. There has to be some space in between for the like charges. Do you understand? Like charges. Thirdly, we are going to have a situation whereby now we have a positive together with the negative charges. Then this one, they will attract. There will be no space in between. Then this is how. Pointing away from positive but towards the negative. You see, like this, like this. For unlike charges, they will attract. Now let us move to the formula of electric field. It is so simple. We have E equals to FQ, whereby our E is our electric field, F electrostatic force, then Q charge. Then now our E, it is measured in N per coulomb, then our force Newton, then C, which is our charge, coulomb. It is so simple. Then now another thing that you have to bear in mind is that, let's say if I have 1 microcoulomb and 1 nanocoulomb together with 1 picocoulomb, how are we going to convert these things to coulomb? For micro, you simply multiply by 10 to the power of minus 6 coulomb, nano minus 9, pico minus 12 coulomb. So simple. Then now let us consider a situation like this. Suppose I have positive together with the negative charge of 2 microcoulomb and minus 5 minus 5 microcoulomb. Then I have this situation. Somehow, let us say we have A, here we have B. Charge B experience a force of 2 Newton relative to charge A. Then how are we going to determine the electric field of charge B? Let us determine the electric field of charge B. How are we going to determine the electric field of charge B? Then now we have to determine the direction for charge B. We have to determine the direction of electric field. We normally use a test charge. A test charge, it is used to determine the direction of electric field. It is always positive. The test charge, it is always positive. If I take a test charge which is positive, it is so small. Let's say if this one is our test charge, né? Somehow it is always positive. Relative to this charge of A, then will our test charge is always positive. Bear in mind, our test charge is always positive. Will it move towards or away from B? It is clear that it will be attracted to negative. Somehow it will be a positive. Sorry, it will move in positive direction, or let me just say it will move to the right. Now we know that the electric field of charge B, it will move towards the right. We always use what? The test charge, which is always positive. Then now we have to convert 5 microcoulomb, which is 5 multiplied by 10 to the power of minus 6 coulomb. Then from here you will then just take your formula. We don't have distance. There is no need for us to focus on distance in this scenario. Then from here, you'll then take your formula, Q, your force, it was 2. Then we have 5 times 10 to the power of minus 6 kilo. Let us calculate. 2, 5 times 10 to the power of minus 6. Then we get 40. 400,000 watt nanokilo. See, this is how we calculate what the electric field of charge B. We also have another case. Whereby they give us the charge together with the distance. A charge together with the distance. And they ask us to calculate what the electric field of that charge at the certain distance, let's say of P, the certain distance of P. Then for that case, how are we going to work out that one? Firstly, we know that from the Coulomb's law formula, let me consider a situation like this. Let's say somehow I use a test charge together with the test charge. If I use a Coulomb's law to calculate the electrostatic force, is going to be F K Q together with small q, then square R. Do you see? This is the formula of what? Of the Coulomb's law. If now I decide to take this formula and substitute it where I see F. Firstly, let me arrange this one in this manner. F equals to F over 1 multiplied by 1 over Q. Still one and the same thing, this formula. Then now let me substitute my F, which is K Q together with small q R squared. Then I multiply everything by 1 over Q. Do you see Q and Q will cancel each other? This one will cancel this one. Then at a distance, we are going to calculate using this formula. You see, if we have, let's say, a certain distance, then we are going to calculate using, this formula. Then how? Let's say if they give us something like this. Let's say I have A, which is 3 nanocoulomb at a distance of, let's say, 4 centimeters. Then you are required to calculate what? The electric field at point, let's say, point X. Calculate the electric field of this charge at point X. How are we going to use this one? Bear in mind, we don't have a force, but we do have a charge, which is 3. Then, now, the situation has changed now. We have a distance. It is different from this one. From this one, the first one. Now we have a distance. We no longer have a force. Then we are going to use this formula, which is K proportionality constant Q divided by R squared. Then from here, we will then say, obviously we are going to start by converting everything, which is going to be 3 multiplied by 10 minus 9 for our Q, obvious. Then Coulomb. Then let us divide our 4 by 100, which is going to be 4 divided by 100. Don't forget, from centimeter to meter, we divide by 100. We get 0.04 meters. Here, kilo. Let us calculate now. Oh, I don't have space. K, you take this formula, K Q R squared. Then your K is 9 times 10, 9. Your charge 3, 10 minus 9. Then your R is 0.04. Then you write a square. I don't have a space. I'll write my final answer here. Then which is going to be 10, 9, 3 multiplied by minus 9 divided by 0.04 square. Then we are going to get, let me double check. Yes, we are going to get 16875 nano divided by coulomb. Then let us determine a direction then from here. Then in which direction will Q act? Then we also use what? A test charge at point X. You simply assume that you have a smaller positive charge here relative to 3. In which direction will this charge move? Obviously they will repel each other because the test charge is always positive. It will move towards the right. Then we say right. Ooh. Yeah, I don't have any space from here. I only have this one. Then yeah, this was just the introduction of what? Of electric field. I hope you understood. Thank you.